graph into this approach. These scenarios. We'll see that here.
So mapping is very useful in geography, and I don't know how to use Python.
Department, and working on a project on deforestation in Amazon, and so far I'm using that's being able to do this in Python and that loss.
We're going to post up in that, and look into that outside property and into industries.
My name is Penny. I'm doing atmospheric science, so I'm doing some actual work.
Sure. Okay, so I'm going to type this out, so hopefully I won't be going too fast, but let me know if you can't follow along or I'm typing out something too fast. So I'm going to start out with just like a plain plot, because just in case you catch up with anything. So I'm just going to import my normal stuff like NumPy, Hotlib, and we'll start with just a regular plot. So we're going to use Cartography, which is a plotting library, somewhat not entirely in Python, but partly based on some C code as well, which I'll talk about a bit later. But it provides a nice Pythonic interface that's based on matplotlib, so you don't have to learn too much of a different syntax or a different set of APIs and stuff like that. So normally we would import that as import Cartography CRS. And the reason why we import the CRS library or the CRS subpackage is because generally all the stuff you want to use is in there. But there's some other things for I/O and other things and stuff that you might want to import from Cartography. We'll look at that a little bit later, though. So again, I'm going to start with a simple matplotlib plot that has nothing to do with maps at all. So I just set the seed for the random number generator so that all of you will have the same plot. And then I'm just going to generate 100 points, some randomly spaced points, and we'll see what that looks like. So that's pretty straightforward. Just plot the X and Y position as like a scatter plot. So you have, just 100 points randomly spaced on the figure. So in case you're wondering why I decided to range them from 0 to 360 and minus 90 to 90, of course, those correspond to latitude and longitude range. So I'm going to just rename them. Did everybody get that plot? So we're going to say latitude equals y and longitude equals x. That makes sense, since if you just look at a straightforward projection of it, the longitude is like x and the latitude is like y. So I'm going to go on a slight digression about projections. This is probably the most complicated part about doing maps, is that you got to figure out what projection you want to actually do it in, because there's basically no way to make a sphere onto a 2D plane without causing some sort of distortion. Either your angles will be wrong, your shapes will be the wrong size, the area will not match, etc. Right? So There are some properties that you maybe want to look at. I can never remember what any of them mean, but you can look at the Wikipedia list of projections, and they have what properties every projection has. So some things that you might want to look at is if they're conformal, they preserve angles locally. That means the shape locally is not deformed. If it's equal area, it means that the areas are preserved. So, for example, something like Mercator is not equal area because that's the reason why North America looks gigantic compared to Africa, or Greenland, of course, looks humongous compared to Australia and that sort of thing, when they're not really that different. Equidistant means that some distances from a certain point are actually the distance that they are. And then mnemonic means that great circle lines are straight lines. So if you look at just a plain x, y, latitude, longitude plot, the straight lines are not straight lines on a globe. So there are several options available. If you look at the link there, I mean, there's a bunch of plots with all the different types of things. I'm just going to go with the straightforward first one, which is plot carré. It's also known as equirectangular or equidistant cylindrical. Basically, it just says plot my latitudes as y and my longitudes as x. It really doesn't do anything, but it's a good first step to see what it looks like. So in order to do that, what I'm going to do is go back up here and just copy that stuff. So in order to do that, at the add subplot thing line, I'm going to add a projection keyword and add CCRS dot and look at it, not much has changed. Pretty much the only thing that's different is that the X and Y ticks are gone. But the actual difference is that your axes class is now has methods that allow you to do stuff that you would want to do when you're making a map. So let's get rid of these extra things. So what you might want to add is add some coastlines. So if I add ax.coastlines now I have a plot that has something, usable. You can see where everything is within the globe. This is your straightforward set of coastlines. It doesn't show countries or anything like that. It's just a nice outline to show where you are in the globe. But of course, that's not really anything too difficult. Let's add some land. So I want to add ax.stock image. Why it's spelled without the A and the E, I don't know, but if we run this, we now have a background, so you can see, that's what it looks like all over the globe. I'm going to add one more thing, which is grid lines. Which is ax.grid lines. And it's not that grid lines. I can actually turn on the labels, but I'm too lazy to write that out, so I won't. But I won't write it every time, but I can add row labels equals true. And I have labels on there now. And this time they're in latitude and longitude. And it's something that looks good for latitude and longitude, as opposed to if you just plotted it directly, you might have just something in the range that between, say, 0 to 10 or something like that. It might annotate it between 0 to 10, but this tries to choose latitude and longitudes that look good as latitudes and longitudes, as opposed to just a nicely spaced set of things. So let's get these. If you look at help for that. I have no idea what any of this stuff is talking about, but if you look here, see there are two arguments. One is central longitude and one is globe. Globe I'm not really going to go into, but basically what globe says is what your actual, I forget what the term is now off the top of my head, but it says what your radius of the Earth is and what sort of higher level changes are involved in that. So if you're talking about WGS 84, then it might be whatever layout was set for the geoid height in 1984, or you may be looking at some North American datum, which has some specific layout for, say, North America, but it's not very good at approximating the actual topography of Europe or something like that. So if you know what I'm talking about, then you'll know what's going to be used there. But I'm not really going to go into detail on that, because it really, for the plots that I'm going to show at like full scale, it really doesn't really make any difference. But if you're looking at some smaller scale details of, say, some small islands, and if you have the wrong globe, then one raster diagram may not line up with another. So let's get rid of all this extra blank space. So I'm going to just copy this here, and we'll try a different. Projection. I'm going to say the TO latitude is 43.660924. So the thing to remember there is that east is positive. And these I just picked out of Google at some time. So anyway, so I'm going to pick a different projection. I'm sorry, azimuthal. So azimuthal equidistant is a plot that centers on one point. So all points on a circle are the same distance away from that point at the center, and all angles from that central point are correct. But any angle anywhere else is not correct. So it shows you sort of like a radar map of Toronto kind of thing. So it tells you things in relation to the one central point, but not any other points together. So I'm going to pass central latitude here. I'll put it next to mine. Central latitude equals geolat. And central run that, and after a second or two, broadcasting is very slow apparently, we get this, which looks nothing like the plot before, and doesn't even look like it makes any sense, because suddenly we lost all the continents. And this is actually an important thing in Cartography, and it actually makes it very powerful, but also it confuses people when they start going from plot array to other projections, is that Cartography allows you to plot things from one projection to another projection. So the starting projection does not necessarily have to be the same as your map projection. And it doesn't have to be latitude and longitude. So in other words, you can get a data set from somewhere that is already projected as in Mercator, for example, and you can input that and say this data started in Mercator, and then your map projection doesn't have to be Mercator anymore. It could be azimuthal equidistant, like what I'm doing now. The thing about that is, if you don't say what the input is, it's assumed to be in the map plotting projection. And the problem with that is that when you convert to map plotting projection, the units are in meters, because you flatten the Earth into meters. And you see my points were all in degrees, which is from 0 to 360. And the Earth is 40,000 kilometers diameter, so, or sorry, yeah, circumference, I mean. So this section of points is really, really small compared to your entire map. So that's why you end up getting just a almost blank looking map. So what I'm going to do is I'm going to copy this and paste it over here. And what I do is I add here the transform keyword geodesic. And what that means is that my input x and y are actually in latitude and longitude and not in the map projection. So if we do that, we have a working map now. And now you see Toronto is somewhere over here at the center of the map. And all of the points are given in the projected space instead of in the middle of, like, right here. The original plot from before just scrunched all of the scatter points all the way into a little spot right here. At most 360 meters away, so basically like outside the building, not really actually the entire globe. So, but yeah.
Maybe I'm a bit confused. The landmark projection is called Vectorized, but this is how geodetic. What's the difference?
I will actually answer that in a second. So, in fact, that's my next question right here. So, what I'm going to do is plot something. I'm going to get rid of these. Put it some other place. So, make it bigger. I'm going to plot one in black gray and one in geodesic, and hopefully you'll see the difference. Let's make it a little bigger. And the other thing I need to add is, so by default, it will try to fit the smallest area that's in the plot. So if you use ax.set global, it will show the entire plot. So if I do this, you see here's the difference between the two. So plot carré is an XY, is latitude, longitude on a map. So what it's saying is the straightest line is the straightest line in XY or latitude, longitude space. Whereas geodetic says what's the straight line on a globe. So
This is basically just how to interpolate.
right, yeah.
So what the scatter plot is.
For scatter plot, it made no difference. So when you're doing lines or you're doing images and that sort of thing, you want to have it interpolated in the correct way. So geodetic will show you that it's on a sphere, whereas plot carré will show you it's on a flat map that you mapped out. So the other thing I wanted to point out, which kind of is exemplified by this, is that you can always use the same matplotlib methods that you would normally use. This is in contrast to a different library called basemap, where you kind of have to do things a little bit differently and sort of you have a transform as the map, or transform to the map, and it's not necessarily all tidy. Whereas Cartography, you just use the regular plot or scatter methods that you would use in matplotlib. And the only difference is that you have to remember to specify the transform for where it starts. So in a way, it's a little bit tidier. Fortunately, there's a real dearth of anybody who is interested in cartography and working on Python. So not necessarily all of them are exactly the same in features, but you know, maybe people who are interested here will start contributing. You know.
Did they modify the axis on that?
Yeah, so it's a geoaxis. So if you check, actually, if you go back up here, and we look at the original one, this is your regular matplotlib axis subplot thing. Whereas here, it is a Cartography geoaxis subplot.
Okay.
So it basically wraps all of the things that are in matplotlib.
So this is a chart plot of the...
Right. Yeah. But anyway, that's getting into too much detail. We don't need to really worry about it. So I'm going to change up what we're plotting a little bit. I'm going to plot Canada. So I picked some arbitrary range of directions here. So I'm going to go the east side of Canada, 63 degrees west. So what I'm going to do is change plotting projections to the Lambert conformal conic projection. This is the one used or recommended by StatsCan. And at this specific, these parameters. It doesn't really matter what, I'm just trying to show you how things change. So for this projection, they're defaults, but there are two parameters you might want to change. The one is the central longitude, which is where it's the center of the map, and the other is the standard parallels. And standard parallels are basically saying which latitudes are going to have some desired property. Maybe it's equal area on that line, or maybe the scale is correct for that line, etc. So let's add a figure. And what we'll do here is to limit the range, I'm going to use ax.setExtent. But that is basically the opposite of set global. It sets it to a smaller area that you want. So I'm going to set, so it goes by x direction and then y direction. So start with the x, end of x, and by the end of the y, which is again longitude and latitude. Right. I'm going to put the stock image again. Those lines, sure. And we have a nice map of just Canada. Well, mostly just Canada, a bit of the US. One of the things you can see here, though, is that the stock image is not very high resolution. There's a lot of pixelation if you look at it on your screen. That's because it's really only meant for a global sort of scale image. It's not high resolution. The same with the coastlines. The coastlines are rather sparse. They're probably I think they're at 110 million scale, so every meter on a map is 110 million meters. So obviously, there's only so much detail you can get out of that. So what we want to do is try and get some alternate features there. So hopefully, where did my mouse go? Oh, there we go. Hopefully all of you were able to download or run the script, but if not, it should still work, but that depends on if the Wi-Fi is still working. So I'm just going to copy that, and instead of putting coastlines and the stock image, again, I said there was more than one thing in Cartography, so what we're going to do is import the feature part of the library. What this contains is a lot of vectorized features that you might want to put on a map. So lakes, country borders, that kind of thing. Now what I'm going to do is going to say ax.add feature. Yeah, a little bit. I don't know what's going on with that, but anyway. And for example, and now you have a land mass there, just the outline though, or just the filled area. So what we might want to add is and over top of that, you might want to add lakes, for example. No, I've already got it cached, so it shouldn't be slow because of the internet. I think it's just because I'm streaming live streaming the thing that it's kind of slow. Normally, I wouldn't have to wait this long, especially once it's cached. I mean, the download is not that big. It's maybe a couple megabytes if you're using the high resolution one. But once it's cached, it's actually much quicker. Like the slowest part is when you're trying to reproject images, like the stock image when I was showing you the earlier one into. It's kind of slow because it has to reproject the entire, like all the pixels of the image, right? Whereas this is a vector format, so it's a lot easier to reproject. You just have to reproject the outline of it. So if you're doing stuff that doesn't involve high density like maps of stuff, but you're looking at GIS data, for example, it's reasonably fast. It's not normally takes that long. So I don't really know why it's going so slow. I think it's just because of the streaming to you.
Is there an easy way to download all the feature data?
Yes, I can show you that at the end. Yeah, I really do. Yeah. So what I'm going to do is Scary stuff. Okay. Okay, so yeah, that's it. Well, my laptop is like completely what's going on. I think it ran out of memory. But anyway. What I was going to say is that you can add ocean